Alrighty, now what I'm going to do in this mini lecture and at least one more after this is cover some material related to Chapter 8. But actually the way I'm going to introduce you to Chapter 8 is by doing a review of Chapter 7 and starting to show some of the linkages between Chapter 7 and Chapter 8. Let me remind you that the two key takeaways for Chapter 8 is we're going to learn how to calculate and work with a confidence interval. We're also going to learn how to calculate the sample size. Okay. Now, coming off of Chapter 7, we learned that it's less likely to draw samples that have average values far from the mean rather than to draw a single observation that's far from the mean. Okay. So this is the key gain in Chapter 7 compared to Chapter 6. We also learned in Chapter 7 that x bar, the sample mean, is a point estimate of the population mu. Now here's where I want to begin to weave into some material that will be relevant in Chapter 8. Through Chapter 6 and Chapter 7, we're operating as though we know what the population mean is. Actually, most of the time, we don't know what the population mean is, and that's why x bar as a point estimate of the population mean becomes so important. Like, we know that the average IQ of people in the U.S. is 100. That's not a controversial issue. So there's an instance where we know what mu, the population mean of IQ for people in the U.S. is. But again, most of the time we don't know mu, and that's why an estimate of mu becomes so critical. And then in Chapter 7 what we do is in Chapter 8 what we begin to do is we migrate from what I call a quote-unquote mere point estimate of the mean, in other words, x bar. So we migrate from a mere point estimate of the mean, which we learned in Chapter 7, to an interval estimate of the population mean mu in Chapter 8. So again, to reinforce the point, in Chapter 8, given that most of the time we don't know what mu is, being able to have an interval estimate of the population mean is advantageous over just having a point estimate in the form of x bar. Okay? And while it's intuitive for most people to understand the notion of an interval estimate, what we do in Chapter 8 is we actually learn how to compute numerically, or from an empirical standpoint, the interval estimate. And again, I show this distribution down here, but notice here that rather than having mu at the center point on the graph, I have x bar, and I note that this x bar is just a point estimate of the population mean, because again, most of the time we don't know what mu, the population mean, really is. Now, this is material that you should be familiar with already, but let me just real quickly take you through this. In Chapter 7, we learned this formula here. Okay, we learned this formula here to calculate the probability of a sample mean being at some location on our normal distribution curve. And then in Chapter 8, we get introduced to this formula here, and what you'll see is this term here, z times sigma divided by the square root of n. That's what I'll refer to as the error term. Now note, if there was no difference between the sample mean, x bar, and mu, the population mean, if these were equal to one another, our error term would be 0. Okay? So again, z times sigma divided by the square root of n is our error term, and our interval estimate is really comprised of two parts, our point estimate and our error term. Okay? And this is what we use to establish whatever this value is right here. We use this to establish the lower bound and the upper bound. And your lower bound and upper bound are equidistant from your point estimate. Now, again, just to kind of reinforce our segue from Chapter 6 to Chapter 7, then I'll tie this in with Chapter 8, is if we want to calculate the probability of one person having an IQ of at least 105, that probability is 0.31. But if we take a sample of 16 people and calculate the probability of a sample of 16 people having an average IQ of 105, that probability is only 0.12. I may have misspoken earlier. The probability of one person having an IQ of at least 105 is 0.38. The probability of a sample of 16 people having an IQ of 105 is only 0.12. But again, the tie into chapter 8 here is, here it's not controversial in terms of what's mu, because we have just huge amounts of data to show that it's 100. But most of the time when we're working with data in business, we don't know what mu is. So these estimates, to be able to move these, or I'm sorry, these probabilities, to be able to see that the larger the probability, the larger the size of a sample, the less likelihood we have of a sample mean being highly discrepant from the population mean, just keeps getting smaller and smaller and smaller. Okay, and then in the next video, what I'll do is I'll actually begin to work with the calculation of an actual interval estimate to build from where we are right here. Thanks.